There are many ways to build counters. We will focus mostly on describing counters using their behavioral. However, before we do that, I think it's important to pause a little bit and discuss the concepts of asynchronous and synchronous counters. I will actually explain the difference using a couple of example counters. So let's get started. We're going to start with asynchronous counters. So the simplest counters can usually be built by cascading a few flip-flops. So this figure here shows me a few cascading Tflipflops. There's specifically 4 of them. So this figure shows me what we call an up counter, okay? Because it counts up, and it means that it counts from 0, 1, 2, 3, all the way, of course, to 15. And it's constructed using Tflipflops. And the simplest counters can be constructed using Tflipflops. You can construct it using Tflipflops, but Tflipflops are simpler. And just as a quick reminder what a Tflipflop is, a Tflipflop is just a flip-flop that has one input and it's called T. T usually stands for toggle for a reason that will become apparent in a second. And a clock, and of course it gives me some sort of an output, and we can call that output whatever you want. You can basically call it Q and Q bar in here, or even Q prime. So according to the characteristic table, it shows me the following. If T, this here, is set to 0, it's basically the Q will not change its position, or it will not change its value at all. So there's no change condition. However, if you put 1 in here, then Q will be complemented at every clock cycle. It just toggles, and that's why we call it a T flip-flop. So if T is 1 and the current value of Q is actually 0, the next clock around you're going to see that 0 becomes a 1. And the next clock around that will become a 0. As long as you keep this as a 1, it just flips between the values. So that's how a T flip-flop works. So back to the asynchronous counter. So in this asynchronous counters, I'm using 4 of these T flip-flops and I'm specifically cascading them, connecting them one after the other. So this counter should count as expected between 0 and 15 because I only have 4 counters in here, so I have 4 bits, and that's why 15 is the maximum number. If you add more flip-flops, you're going to get more counts. For example, if you add a flip-flop in here and you cascade it, you're going to go to, I believe, 32, from 0 all the way to 32. So the key word here is asynchronous. Why do we call this counter asynchronous? And it turns out that because the clocks of every flip-flop is connected to a completely different signal. So the way that this counter is built is by connecting the Q bar or Q prime of a previous T flip-flop to the clock input of the next one. So this clock in here and this clock in here will get completely different signals and they're out of sync, and that's why we call them asynchronous counters. So let's see how it operates before we actually go and build them. So for the sake of example, we're going to just start by saying, okay, we're going to start with the reset condition where the first number is actually 0 decimal. So what happens next? Well, I will have a clock signal in here. And according to this here, I have 1 at the toggle. So all of them are connected to this one. All of them are connected to this one. So all of them will be toggling when they get a clock signal or a clock edge, specifically a positive edge in here. So once a positive edge comes to this one here, you'll see that the value for the first flip-flop will actually toggle. So the value in here is at 0, but then when it toggles, and of course this is a 1, so when it toggles, that means this will become a 1 and this will become a 0. Okay, so this is a 1, this is a 0. Nothing happens here because what we just saw between 1 and 0 is a negative edge, and this is activated by the positive edge. So the rest of the flip-flop will stay at the exact same thing because this didn't change, so this will not change and this will not change. All right, a next clock cycle comes in. So now in the next clock cycle, what happens is this got toggled to 0, and of course this got toggled to 1. So what happens in here is I move between 0 and 1, so this activated the second flip-flop. So Q0 became a 0, and this now toggles its value, and this becomes 1 here, and this becomes 0 in here. Okay, of course, this was a 1 and became a 0, so it's still a negative edge, so this does not get activated, so the rest of the flip-flops here become 0. And as you can see, it is counting. This is 0, this is 1, this is 2, and you can probably figure out that the next count that comes in, or the next clock cycle, you will see that this will be a 1, and because we got a negative edge at the Q bar in here, this will stay at 1, and this will become 0, this will become 0, and you get a 3. So we just counted from 0 to 3, and that's, you can continue it in the same process. It just works that way. So this is how it operates. Let's go and build it in Vivado. So I went ahead and I created a few files in here just to save some time in here. And the first module we're going to talk about is this Tflipflop. So there are multiple ways to construct Tflipflops. Technically, you can construct it with a Tflipflop and an XOR, but this detail is not important. So I'm just going to describe its behavior here so that I can show you how I describe its behavior. So a Tflipflop, as the figure in front of us shows, it takes a clock, it takes a T, and you can get a reset. I don't show it here in the diagram, but generally you will want a reset for your flip-flops. And then of course we have a Q, and of course we can add Q bar if we wanted to, or Q prime. And then the way we're constructing it is, as usual, we're gonna split the next state and the current state and the registers. So the first always statement here is just the register itself. So it's usually activated by a positive edge of the clock, or because we're using an asynchronous reset in, and we're just gonna do this. This is just a typical one, a typical register. And then the next state is just based on the value of t. If t is asserted, we just basically take the current value and we just flip it. Other than that, we just keep the current value, and that's what the next value is, and this gets updated in here. And of course the output logic is just renaming the current value to Q so that we can output it to the outside world. Now there's a little addition in here that I skipped over it very quickly, and this is actually what we call C2Q delay. This is for simulation purposes only, and I'm going to show you, and I'm including it in here because it will affect my simulator, it will affect my simulation. But when you actually take this code or this Tflipflop and you use it within your FPGA code, this is meaningless and will do nothing. Okay, what do I mean by it's meaningless? Well, this is just a local parameter, but the way I'm using it is actually in here. What I'm doing is I'm saying, okay, I want to create some sort of an artificial delay between taking the next value and updating the current value with it. And as it turns out that all flip-flops have timing parameters. We will go through these timing parameters later in more details, but for now, what you need to know is the following. Usually you have an input at T, and you have some sort of a clock, and you have a Q. And as it turns out, a clock comes in, it'll take the flip-flop some time to reflect some sort of a change at the output. And usually this is what we call clock to Q, okay? So from the positive edge or the negative edge, from the active edge of the clock, the active edge comes in here. There is some sort of a delay for the Q to actually update it with the current value or the proper value. And this is what we call clock to Q. And this is what C2Q stands for. It's clock to Q delay. So in here, what I'm saying is I want from the positive edge of the clock till Q gets updated with the proper value to be a delay of 2 nanoseconds. Again, this is just for simulation. If you actually put it on your FPGA, you will get a delay, but it will be different. It will be based on the actual physical flip-flop used on the FPGA. In here, just for simulation purposes, I'm going to say it's 2 nanoseconds. And it's nanosecond because the time scale here is set to 1 nanosecond. Okay, we'll see that effect shortly, and I'll change that number just to show you how important that number is. All right, so we constructed the Tflipflop, and then I'm going back in here and I created an asynchronous up counter. Again, this is an up counter. I can easily create a down counter by taking that Q and connecting it to the clock, and taking that Q and connecting it to the clock, and I'll get a down counter that go 15, 14, 13. But anyway, that's beside the point. The point in here is actually to construct asynchronous counters. So what's an asynchronous counter in here? It actually takes a clock, and that's what you see in here. And of course, there's a reset. I'm not showing it in here, but I need some sort of a way to reset all these values to zeros. If I actually, with simulation and actually in general, you don't know the starting position, but so we're gonna add this reset, and we just connect it to all the flip-flop. And of course, I have a 4-bit in here because I'm building this particular specific counter. Of course, I can expand it if I wanted to, and I can make it more generic. But the point in here is I just want to show you what asynchronous counters are. And the code is pretty straightforward. It's just 4 flip-flops. I'm just instantiating 4 instances of that Tflipflops, and I'm just connecting it based on this diagram. And you can follow it. You can pause the video and just follow it on your own. All right. Then I want to test this asynchronous counters to show you how it operates. So in here I created a test bench, and in the test bench I just instantiated .module, and I created a clock in here just for the simulation purposes. And then what I did in terms of stimuli, I just issued a reset for a very short period of time, which is 2 nanoseconds, so that I make sure that all the flip-flops at the beginning are zeros, and then I left it run for like 200 nanoseconds or so. So when you run that simulation, you're going to get this particular diagram in here. And taking a look at this diagram, I have the clock. So the clock is as expected. I'm creating a clock that is 10 nanosecond. That means or 10 nanosecond period. That means it's 100 megahertz. And then as the simulation test bench in here, let me just put it down so that you get to see it. So in here, the simulation test bench, you're going to see that the reset was issued for 2 nanoseconds. That's exactly what you see in here. So at 2 nanoseconds, I just put the reset for a short period of time, so my output is 0. Now taking a look at the output of the flip-flop or the counters itself is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It goes all the way to 15 and it goes back to 0, 1, 2, 3. So it is working properly. This is how I expect it to work. However, there are these little tiny details in here. Okay, so let's see it. There's a couple of problems in here that I don't like. If you see it, the length of 1 is actually between 7 and 17, so it's lasted for 10 nanoseconds. However, if we take a look at 2, it lasted between 19 all the way to 27, so it lasted for 8 nanoseconds. So the numbers, depending on which number you're at, it doesn't last at the same exact period. And if I actually zoom in just to see what these ones with no numbers are, they are actually numbers. They were just hidden because they're smaller. So let's take a look. The output of the flip-flops, or the outputs of the counters, is 0, 1, and then goes back to 0 and then 2. So this is what we call a glitch. So there are glitches in here. Okay. The same goes after the 2. It goes to the 3, no problem whatsoever. But before going to the 4, it actually went through a glitch in here. So the 2 glitches actually shows me 2 and 0. So let's see what's happening. So the way I'm going to actually do that is I'm going to expand that number. And I'm going to take a look in here exactly, because this is what I'm showing you. It's actually going from 0 all the way to 4 as well, not only to 3. So initially, I have that reset. The positive edge of the clock is in here. Okay, actually, yes, this is the positive edge of the clock. And what happens is my Q0, 1, 2, and 3, they were all at 0. And then a positive edge comes in. Because of the first positive edge comes in, I expect Q0 to be at 1. But because we did that clock to Q delay, you'll see that it'll take a couple of nanoseconds after that 5 for the first Q0 to get updated. So this should be at 7, and it is at 7. So it got updated after 2 nanoseconds because of the clock to Q. A clock comes in here. It took 2 nanoseconds for this output to be outputted in here. All right. Next, the next positive edge of the clock is in here, and we know that this will take a couple of nanoseconds to actually go down. Okay, and that's exactly what happened. So this went down, and of course, because this went down, this is that particular case. So we had the 1. Now this went down. Of course, this has to go up, which is Q2. And because of the clock to Q delay, so this one took from 15 to 17. That's 2 nanoseconds. Another 2 nanoseconds, which is 19. And we got like basically the Q1 to be updated. But between these two couple of delays, what I got is I got both of them to be set to 0, and that's where I got the glitch. So the first glitch appeared is because it took some time for this to get updated, and then it took this some time for this to get updated. So the time we had to wait between, this is the active edge of the clock, we had to wait for 4 nanoseconds to get the correct number. Okay, so that's the first glitch. You can follow the rest of them as well, and you will see that in here I'm getting, this is the active edge of the clock, and which is at 35, and then it'll take me about from 35 to 41. It's about 6 nanoseconds because there's 2 and 2 and 2. Each one of them will result in 2 nanoseconds. And the glitches are kind of random because sometimes you need to flip a flip-flop, others you don't. In here, we got a couple of numbers because the 4 is you had to flip this flip-flop, you had to flip this flip-flop, and you had to flip this one. So that's a problem with asynchronous counters. They're filled with glitches. So the number doesn't last as long as I wanted. And also, if I'm dealing with some sort of a fast circuit that is actually operational at faster than the clock speed, I'll be able to read these glitches, and that creates a problem. So let's move into synchronous counters. And by the way, asynchronous counters are sometimes called ripple counters because the delay has to be rippling through that here. Actually, let me just pause for a second and change the delay a little bit. I forgot to change the delay, so let me just do that. What I wanted to show you is we can definitely go and change that artificial delay. And again, this is for simulation purposes. So this delay was okay, and the counter actually operated. So when I zoomed out and did this, the counter operated 0, 1, 2, 3, because the delays, the maximum delay I can expect is 1, 2, and 3, and 4, which is 4 times 2 is 8 nanoseconds, but my clock period is 10 nanoseconds, so it's still within my clock period. So I'm changing the maximum change that can happen within my clock period, so I'm fine, and that's why I got that counter to work. However, in an extreme case, maybe my flip-flop the clock to Q is actually 6 instead of 2, okay? So in that case, if I have 6, that means this can be a maximum of 6, this can be a maximum of 6, and so forth. So what I have is 6 times 4, which is 24 nanoseconds. It's much longer than the clock cycle. So if I actually go and run, I'm going to save this here, and I'm running the simulation again. What I did is I just artificially made the clock to Q a little bit larger, just so to see the effect. You'll see that that asynchronous counter will break. And this is one of the problems with asynchronous counters, is they are technically slow. You can't operate them at a faster speed. So we're going to go in here, we're going to zoom out, and you're going to see that we got a 0, a 1, and then a 0 and a 2, and then a 3, and then a 2 and a 0. You can see that I didn't even see the 4. Like I can zoom in here and show you this is not a 4, it's a 1. So it completely skipped the 4, and then 4, 6, 7, and then 6, 4. It's like it stopped working because that delay now is longer. So it's rippling the effect, for example, like this one here, it's rippling to that, but then the next clock cycle comes in, and this starts changing before this gets updated, and that's an issue, and that's why we can't use asynchronous counters with fast circuits. Okay, so now we can move into synchronous counters, which should solve this particular problem. So synchronous counters can be built in a very similar fashion to asynchronous counters. Again, we're going to just show it with 4 bits, but synchronous counters work in the, this particular one is an up counters. I have 1, 2, and 3, and 4 because I have 4 flip-flops. I can go from 0 to 15. Okay, and again, it's an up counter. I can definitely create a down counter in the same manner, but in here, I just want to show you synchronous counters. So synchronous counters, or this particular counter is called a synchronous counter because, as you can see, all the clocks, this one, this one, and this one, and this one, they're all operational using the same exact clock, and that's why we call them synchronous. So they all get updated at the same exact active edge. They all have the same clock, and this is usually a good thing to do when we're designing synchronous systems. Okay, so now how does it operate? Well, we can see the example like we did before. So I'm going to start with the 0. Well, let me just do that here. So we're going to say that the value is 0, which means this is 0, 0, 0, 0. And then how it's operational? Well, I have the Tflipflop here at 1, and then next Tflipflop, instead of connecting that Q or the Q prime directly to the clock, what we did is we took the output of this one and the enable of this one, we put them through an AND gate and in here. So what's happening? Let's see. So this is a 1, okay, so we goes in here, and then this one here is Q. If at the current location it's at 0, so the output is 0, and everything else here stays at 0, and that's where we have zeros in here. So everything stays the same. But then the next clock cycle comes in, so I have a clock in here. So what happens is this is set to 1, so this will toggle its place. So by toggling, that means this goes to 1, and I'm at this particular moment, I don't care about Q prime or Q bar because I'm not using them. What I care about is now this is a 1 and this is a 1. Okay, I know that this is here a 1. And this, of course, because at this current clock cycle, like the clock cycle just happened, so nothing will happen at this T0 because it was at 0. It didn't change this to 1 yet. Okay, so what happens is this stays at 0, this stays at 0, this stays at 0. But the next clock cycle comes in, this is at 1 and this is at 1, so this is actually activated. So the input for the second toggle flip-flop is actually a 1. So what happens is this is a 1 and this is a 1. So this will toggle its number and this will toggle its number. So this will become a 1. So toggling this and 0 and 0. And as you can see, I'm counting 0 and this is 1 and this is 2. And you can follow, of course, because we toggled this 0 in here. So now this one here, there is a 0. Okay, so it stays, and this will stay at 1. So the next clock cycle comes in. This is at 1. This was at 0, so it becomes a 1. And then this will stay as is because its input is 0. This is 1. This is 0, 0, and we got 3. And that's how a synchronous counter works. All right, so let's see how we can actually build them in Vivado. All right, so we're going to be using the same exact flip-flop. So we're going to start with a delay of 2, okay, 2 nanosecond delay, and then I'm going to show you how we actually build that synchronous, and I did it to save some time, and it's really straightforward. It's just following this particular diagram in here. And specifically, I have 4 flip-flops that are just instantiated this way, but what I'm doing is in front of every flip-flop, there's some sort of an AND gate in here. Okay, so the first one, it's telling me in here. So you see, this is the first AND gate. This is Q0 and the enable, okay, from Q1 next, which is this one in here. and the first Q1 next or Q0 next is this one here, was 1. I'm just following that diagram. I just these assign statements are just to do these AND gates in here, and I started with an assign statement in here that it's basically just assigning the Q0, which is here, the next value to 1. Just a quick comment, we can make this as an external signal as an enable to enable the whole counter if we choose to. So instead of just assigning it to 1 in here, we can just add a signal in here as an enable, and we connect it to it, and that will work. But anyway, that's beside the point. Now I just want to see how it's operational. So I went ahead and I created another test bench. So this test bench in here is exactly the same as the previous one. It's exactly the same as the asynchronous counter. All I'm doing is I'm just issuing a reset for a short period of time, and I'm letting it run for quite some time. So let's take a look at the output in here. So the output is, as we expect, 2 nanoseconds to become that 0, and then it goes 0, 1, 2, 3, 4, 5. And as you can see, because they are synchronous counters, first of all, there are no glitches whatsoever between the numbers. I don't see anything. Even if you zoom in here, you'll see that it goes 1, 2, 3, and 4. So there are no glitches whatsoever. And the other thing is the delay between, or the period at which a number stays active is exactly the same everywhere. So this is here is going between 11 to 21. That's 10 nanoseconds. And I'm expecting this to be at 31, and this is at 41, and this is at 51. Exactly, that's what's happening in here. They're all exactly the same, and it goes between 0 all the way to 15. It's counting up, and then it goes back, it rotates, and it becomes 0, 1, and 2, and 3. So that's how synchronous counters work. So they did solve that problem. Frankly speaking, even if you go in here and say, okay, the delay is 6 nanoseconds, the thing about it is that delay is not being propagated. So I'm going to run the simulation in here while it's running. I'm going to explain it to you. All of them, 6 nanoseconds is still less than 10 nanoseconds, which is the clock. But because I'm dealing with synchronous and all of them are operational at the same exact clock speed, so this is a 6, this is a 6, this is a 6, this is a 6, they don't get accumulated. So if I'm taking a look at that, what I will see is the only difference is the delay between the active edge of the clock and the next value. So this is 5, the next value should be at 11, okay, because it is just delayed by 6 nanoseconds, but the number still works and everything works exactly the same. As you remember, the 6 nanoseconds actually broke the asynchronous counters, which tells me that asynchronous counters cannot be used in fast circuits. All right, so just to summarize, what we've done is we've seen synchronous counters and asynchronous counters, and I've showed you synchronous counters and I told you they're better, they don't generate glitches and whatnot. I just want to make sure that, to mention the following, synchronous counters still have some sort of constraints as well. So asynchronous counters, I said like, oh, you can't use them in high frequency circuits or high speed circuits. Asynchronous counter still uses or still actually introduce or delays or bugs. So for example, this one in here has to actually go propagate through this AND gate and this AND gate and this AND gate. So what happens in here is this one, or the enable, if we connect this one to an enable signal, has to propagate through different AND gates. And this is usually what we call in here, this one here, the one that you see is what we call the critical path, okay? It's a critical path, and we're going to be talking about this when we talk about timing. It affects the performance of synchronous circuits. So synchronous circuits still have some sort of a limitation in terms of speed. This particular path will affect the maximum clock frequency I can operate at. And it all depends on how much delay does this AND gate or this AND gate or this AND gate give me. Usually it's much less than actually the clock to Q. But anyway, that's beside the point. The point I'm trying to make in here is synchronous counters still have some issues, still have some speed issues. Of course, you can tell me, well, we can solve this issue by creating really big AND gate at each one and just feeding this directly to it without actually having to pass through one AND gate and another AND gate and another AND gate, which is fine. You can definitely do this. The final AND gate will have multiple inputs, which we usually refer to as a fan-in, and it can grow really large, and there are certain limitations. Anyway, why did I show you the differences between synchronous and asynchronous counters? I did show you that because of the glitches. Sometimes you take a look at your code and you get glitches. Just make sure that you're using synchronous counters. If you are using asynchronous counters, they might be the source of these glitches. Not always, but chances are they are. Not to say that asynchronous counters are not always bad. Okay, so sometimes asynchronous counters are used because they're simple to build. So for example, in synchronous counters, there's no need to use these AND gates in here. So if there are no need to use these AND gates, they're simpler to build. And because I have less AND gates, I mean, they might be lower power. So if I'm actually in an application that doesn't need high speed, but it's actually sensitive to power, so I might use asynchronous counters. And also for certain applications, maybe I just don't want to overcomplicate myself. If that delay of 10 nanosecond and the glitch just lasts for 6 nanoseconds, but my application is a human being just looking at a number, chances are you're not going to see that 6 nanosecond glitch. You're just going to see it counting 0, 1, 2, and 3, and so forth. So we're not dealing with high-speed circuits at that point.